The water is moving, not in a trickle, not in the thin seasonal seeps that will later puzzle the scientists who point their instruments at this world from a distance of hundreds of millions of kilometers. Real water, deep water, mineral-rich and warm at its edges where the volcanic heat still bleeds upward through the fractured basalt. The surface of this world, 4,100,000,000 years ago, carries lake systems that stretch for hundreds of kilometers. The lowland plains to the north hold water in volumes that some estimates place higher than the Arctic Ocean, on a world that does not yet have anything calling itself a civilization, or even a cell. This world is Mars, and it is not the Mars anyone living today would recognize. The sky above these lakes is not the thin, butterscotch-coloured haze of the Mars captured in rover photographs. It is denser. Carbon dioxide and water vapour and nitrogen fill an atmosphere thick enough to keep surface temperatures in ranges that liquid water can exist not just in pressurised pockets, but across open plains, under an open sky. The sun is smaller from here, about a third less intense than it appears from Earth, but the greenhouse effect of that early atmosphere compensates. The ground at the edges of the water is dark with wet sediment. Iron-bearing minerals are everywhere, and when they react with the oxygen dissolved in shallow pools, they begin their slow turn toward the red that will eventually define this world in every human eye that looks up at the night sky. Life on Earth, at this moment, does not exist. The earliest confirmed microbial life on Earth, preserved in ancient rock formations in Western Australia, dates to around 3,500,000,000 years ago. The oldest possible traces, chemical signatures in ancient zircon crystals from the Jack Hills of Western Australia, push that number back cautiously toward 4 billion and perhaps slightly beyond. But these are traces, whispers in stone, not confirmed organisms. The Noachian period of Mars, the era when liquid water moved freely across its surface, runs from approximately 4,100,000,000 years ago to around 3,700,000,000 years ago. That is a window of several hundred million years during which Mars possessed the basic conditions that we associate with the possibility of life, and Earth either had not yet produced life or was only just beginning to do so. 50 million years. That is a conservative way of stating the gap. In reality, the overlap and the lead time may have been considerably longer, depending on which estimate for early Earth life you accept. But 50 million years is the number that frames the question plainly. 50 million years is enough time for an entire evolutionary branch to rise and disappear. 50 million years after the last non-avian dinosaurs vanished from Earth, modern whales were already swimming in warm seas. 50 million years is not a rounding error. It is an enormous span of time during which conditions on Mars were, by the measures we apply to Earth, compatible with life, and conditions on Earth were not yet confirmed to support it. This documentary for Sleep will move through that span of time. It will not speculate beyond what the evidence supports, and it will say clearly when a claim is established science and when it is a legitimate hypothesis held by working planetary scientists but not yet confirmed. What it will do is give you the full picture of what Mars actually was during the period the title describes. The geology, the chemistry, the water, the atmosphere, and then move carefully through what the evidence suggests about whether that early Mars could have harboured life, what kind of life that might have been, and what happened to end it. There is no shortage of material. The Mars we have studied with orbiters, landers and rovers since the late 20th century has returned data of extraordinary detail. The rocks read, the minerals speak. The ancient stream beds preserved under billions of years of dust and radiation carry the memory of what moved through them, and some of that memory points in directions that are, at minimum, worth taking seriously for the 2 hours you are about to spend with this story. Before going further, a moment to slow down. You're listening to a long-form documentary designed for the pace of a quiet evening or a slow drift towards sleep. The information in it is real. The science is sourced from peer-reviewed planetary science, from data returned by missions to Mars across more than 5 decades, from laboratory analyses of Martian meteorites recovered from Antarctica and other locations on Earth, and from the accumulated body of comparative planetology that has grown alongside the study of Mars. Nothing in this script is invented. Where a claim is contested or uncertain, it will be labelled as such. The pace will stay steady. There is no rush. If you are curious enough to stay with this through to the end, you will come out the other side knowing more about early Mars than most people who have never specialised in the subject. That is the only promise being made. Now, back to the water. The Noachian period takes its name from Noachis Terra, a large highland region in the southern hemisphere of Mars, one of the oldest terrains on the planet's surface. The naming convention is borrowed from the tradition of naming Martian features after places and people from Earth's geography and history, but that is a detail of nomenclature. What matters is what Noachis Terra and the broader Noachian landscape tell us about what Mars was during this earliest period of its geological history. The evidence for widespread liquid water during the Noachian comes from multiple independent lines of geological data. Valley networks, ancient river valleys carved by flowing water, are distributed across the Martian highlands in patterns that strongly resemble drainage systems carved by rain and surface runoff on Earth. These are not small features. Some of the valley networks on Mars extend for hundreds of kilometers. The valleys show branching tributary patterns consistent with precipitation-fed drainage, not just the linear channels you would get from a single catastrophic flood or from meltwater running along a single path. They branch. They have been mapped in detail by orbital cameras, and their morphology points toward a sustained hydrological cycle. Not a one-time event, not a slow seep, but something more like weather. Rain falling on highlands, running down slopes, collecting in lowlands. The clay minerals found across large portions of the ancient Martian surface add another layer of evidence. Phyllosilicates, the broad category that includes clays, form through prolonged contact between water and rock. They do not form quickly. They do not form in the presence of brief or transient water. When the spectrometers aboard orbital missions began mapping the distribution of phyllosilicates on Mars, the map showed concentrations precisely in the oldest terrains, in the Noachian highlands, in the floors of ancient craters, along the walls of ancient valleys. The clay record is a chemical record of sustained liquid water interacting with Martian rock across long periods of time. On Earth, these same minerals are where you find the oldest preserved organic chemistry. The Noachian highlands of Mars are, chemically, one of the most promising archives in the solar system for evidence of early chemistry, and potentially early biology. There is also the crater record. Mars, unlike Earth, has preserved its ancient craters in extraordinary detail because it lacks the tectonic recycling that constantly destroys and replaces Earth's crust. The oldest craters on Mars, the ones that formed during the period of heavy bombardment that affected all the inner planets, show features inside them that indicate they were once filled with water. Lake sediments, delta deposits at the points where ancient rivers entered crater basins. These delta structures are among the clearest evidence of sustained liquid water. A river delta only forms when water flows into a standing body of water over a long period, depositing sediment in a characteristic fan shape at the point where the current slows. Jezero Crater, which became the landing site for the Perseverance rover mission beginning in 2021, is one of the most studied of these ancient crater lakes. Its delta is visible from orbit. On the ground, Perseverance has been sampling the delta sediments directly, reading the mineral record layer by layer. Jezero Crater held liquid water for somewhere between tens of thousands and potentially millions of years. That is a conservative estimate based on the thickness and composition of the sediment layers. During the Noachian, there may have been dozens of such crater lakes active simultaneously across the Martian surface, each one fed by its own river system, each one accumulating sediment, each one providing a chemically rich, relatively stable liquid water environment. The atmospheric conditions that made this possible were very different from anything Mars has today. The current Martian atmosphere is so thin, about 1% of Earth's atmospheric pressure at sea level, that liquid water cannot exist on the surface. It either evaporates directly into the thin gas or freezes. But during the Noachian, the atmosphere was substantially thicker. The exact pressure is debated among planetary scientists, and there is a wide range of estimates depending on the model being used and the evidence being weighted most heavily. Some models place the early Martian atmospheric pressure at 1 to 2 atmospheres, roughly comparable to Earth's present atmosphere. Other, more conservative models suggest it may have been lower, perhaps half an atmosphere or less. But even the lower estimates are sufficient under the right conditions to allow liquid water to exist at the surface. The source of that early atmosphere was volcanic activity. Mars during the Noachian was volcanically active on a scale that is difficult to picture from the perspective of the quiet, geologically almost dead Mars of today. The The great volcanic provinces, Tharsis in particular, the largest volcanic complex in the solar system, were building during this period. The eruptions that constructed Tharsis released enormous volumes of gas into the atmosphere: carbon dioxide, water vapour, sulfur dioxide, hydrogen sulfide. These gases thickened the atmosphere and contributed to a greenhouse effect that kept surface temperatures warmer than the distance from the sun alone would have permitted. Volcanic activity also heated the ground from below, creating hydrothermal systems where water circulated through hot rock, picking up minerals and energy as it moved. Hydrothermal systems are relevant here because they are, on Earth, among the most productive environments for microbial life. The deep-sea hydrothermal vents discovered on Earth's ocean floors in the late 20th century host ecosystems that derive their energy entirely from chemical reactions, with no dependence on sunlight. Chemolithotrophic organisms, life that eats rock chemistry, thrive in conditions that would be lethal to most of the life familiar from everyday experience. If Mars had extensive hydrothermal systems during the Noachian, and the geological evidence suggests it did, then those systems would have provided not just liquid water, but chemical energy gradients, mineral surfaces for chemistry to organise on, and a degree of protection from surface radiation. The radiation environment of early Mars is worth addressing directly. Mars lacks a global magnetic field today. Earth's magnetic field, generated by the churning of its liquid iron outer core, deflects a large proportion of the charged particles streaming out from the Sun and protects the surface from the worst of the solar wind's effects. Mars lost its global magnetic field early in its history. The exact timing is uncertain, but the loss appears to have occurred sometime around or shortly after the Noachian period. Before that loss, Mars may have had a functioning magnetic field. Remnant magnetic signatures preserved in the oldest Martian rocks suggest that a magnetic field was active during the earliest phase of the planet's history. If life existed on early Mars, it would have had at least some magnetic protection during the critical early window. After the field collapsed, the solar wind began stripping the atmosphere away, ion by ion, particle by particle. This is the long, slow catastrophe that ended the Noachian world. It did not happen overnight. It played out over hundreds of millions of years, and the Mars of 3.5 billion years ago, the Hesperian period, which followed the Noachian, was already a colder, drier, thinner atmosphered world than what came before. But even in the Hesperian, liquid water periodically appeared on the surface in catastrophic flooding events, fed by the release of water stored underground. The transition was not a hard line, it was a long decline. What the Noachian represents then is a window, a geologically defined window of several 100 million years during which Mars was, by the standards we apply to habitability on Earth, a plausible host for life. The question of whether anything actually lived there during that window is a separate question, and the script will move toward it carefully in the sections ahead. But the first thing to establish, and what the geological evidence establishes clearly, is that the window was real, the water was real, the warmth was real, the chemistry was real, and all of it was happening 50 million years or more before the first confirmed life left its mark on the rocks of Earth. The floor of the ancient crater is still warm, not from the sun, which hangs smaller and dimmer in this sky than it does over the world that will eventually name this crater Jezero. The warmth comes from below, from the slow bleed of heat through fractured basalt, from the hydrothermal circulation that has been running through the rock beneath this basin for longer than any single surface feature has existed. Water enters cracks in the crater floor, descends, heats, rises again carrying dissolved minerals, iron, magnesium, sulfur compounds, silica, and spreads along the shallow bottom of the lake in thin chemical plumes that catch the weak sunlight filtering through the haze above. The delta at the western inlet is building, sediment carried by the river that feeds this lake from the highlands to the northwest arrives here and slows, losing the energy that kept it suspended in the current, and settles. Layer by layer, season by season, the delta grows. At this moment in the Noachian, the delta front extends perhaps 4 kilometers into the basin. The river that feeds it drains a catchment area of roughly 15,000 square kilometers of ancient highland terrain. All of that terrain is chemically active. The water that falls on it as rain or snow filters through it, dissolves minerals from it, and arrives at this lake already rich in the raw materials of chemistry. Jezero, during this period, is not an isolated feature. Across the Martian highlands, dozens of similar crater basins hold standing water, fed by valley networks cutting down from the surrounding terrain. Arabia Terra to the north carries its own complex of ancient drainage systems, some of them feeding into one another in chains that suggest a landscape capable of moving water across vast distances. The Hellas Basin, the largest impact crater on Mars and one of the deepest geological features in the inner solar system, may have held a lake of extraordinary size during wet periods of the Noachian, with a surface area potentially comparable to the Caspian Sea on Earth. The Arjar Basin, another large ancient impact structure in the southern hemisphere, shows similar evidence for persistent water. This is not a world with a few damp patches. During the peak of the Noachian wet period, the geological record suggests a planet where water was a significant presence across a large proportion of the surface. The estimates for the total volume of water on early Mars vary considerably, depending on the model, but some reconstructions suggest an equivalent global layer of water, meaning if all the water were spread evenly across the planet's surface, of several hundred meters. That is not as much as Earth's oceans, but it is far from trivial. It is a water inventory large enough to sustain river systems, lake chains, and possibly shallow seas in the northern lowlands for geologically significant periods of time. The northern lowlands of Mars, the vast, relatively flat plains of the northern hemisphere, have long been considered a candidate location for an ancient Martian ocean. The hypothesis of a Noachian northern ocean remains debated, and the evidence for it is less straightforward than the evidence for lakes and river systems in the highlands. But the topography supports it. The northern lowlands sit on average several kilometers below the mean elevation of the Martian surface, creating a natural basin into which water flowing from the higher southern terrain would eventually collect. Certain features along the boundary between the northern lowlands and the southern highlands have been interpreted as ancient shoreline structures, though their origin is contested. What can be said with confidence is that the northern lowlands, during the Noachian, received enormous quantities of water delivered by the catastrophic outflow channels that periodically discharge from the highlands, and that some of that water pooled rather than evaporating immediately. The chemistry of that pooled water is relevant to the question of life. Water on early Mars was not pure. It carried dissolved salts, minerals and gases picked up from the volcanic and hydrothermal environments it had passed through. In some locations the water would have been acidic, enriched in sulfur compounds from volcanic outgassing. In others, it may have been alkaline, enriched in carbonates. The diversity of water chemistry across different Martian basins during the Noachian would have created a range of chemical environments, some more hospitable to prebiotic chemistry than others, and some more closely resembling the environments in which early life on Earth is thought to have arisen. On Earth, the leading hypotheses for the origin of life tend to center on a small number of specific environmental types. Hydrothermal vents on the ocean floor provide chemical energy gradients and mineral surfaces. Shallow, periodically drying pools, sometimes called warm little ponds, a phrase that goes back to Darwin's private correspondence, provide concentration cycles where organic molecules can accumulate and react in ways that dilute open water prevents. Hot springs with mineral-rich water offer yet another setting. The remarkable thing about early Mars, viewed through the lens of the Noachian geological record, is that all three of these settings appear to have existed. Hydrothermal systems fed by volcanic heat beneath crater lakes, shallow coastal zones around lake margins that would have dried and refilled with changing seasons or orbital cycles, hot spring environments in the volcanic regions where groundwater heated by magma reached the surface. Whether prebiotic chemistry actually progressed toward life in any of these settings on Mars is unknown. The evidence does not yet reach that conclusion. What it establishes is that the environmental prerequisites, the raw materials, the energy sources, the liquid water, the chemical gradients, were present on Mars during the Noachian, and that they were present across a range of settings comparable to those invoked for the origin of life on Earth. The mineral record tells some of this story in specific chemical terms. The phyllosilicates found in the Noachian terrains include smectite clays, the same broad family of clay minerals found in some of the most organically rich sediments on Earth. Smectite clays have a layered structure at the molecular scale that gives them a large surface area relative to their volume. This surface area matters because it provides sites where organic molecules can concentrate, align, and undergo reactions that would not occur in open water. On Earth, clay surfaces have been seriously proposed as scaffolding for the early stages of molecular self-organization that preceded life. If organic molecules reached the surface of early Mars, delivered by meteorites and comets, as they were to early Earth, or synthesized through atmospheric chemistry, the clay-rich sediments of the Noachian crater floors and river deltas would have provided surfaces to work with. Organic molecules did reach Mars. This is not speculation. The Curiosity rover, operating in Gale Crater since 2012, detected organic molecules preserved in ancient mudstone sediments that date to around 3,500,000,000 years ago, which is already well into the drier Hesperian period that followed the Noachian. If organics survived in sediments from the relatively less hospitable Hesperian, the wetter, chemically richer Noachian sediments would have been even more favourable environments for their preservation and accumulation. The Perseverance rover's work at Jezero Crater has continued this line of investigation, and the samples it has drilled and cached for eventual return to Earth are specifically targeted at the ancient delta sediments, where the probability of finding preserved organic chemistry is considered highest. The question of what organic chemistry was doing in those sediments during the Noachian, whether it was simply inert chemistry or whether it had begun organising itself into something more complex, is a question that cannot yet be answered from orbital data or from the measurements made by rovers whose instruments, however sophisticated, are operating under constraints that a laboratory on Earth does not face. The sample return mission, if it reaches completion, will bring Jezero sediments to terrestrial laboratories where they can be analysed with the full range of tools available to modern chemistry. That work, when it happens, will be among the most significant scientific investigations ever conducted. For now, the sediments sit in their sealed titanium tubes, cached on the Martian surface waiting, and the ancient lake that deposited them is 4 billion years gone. What ended the Noachian world of Mars was not a single event. There is no asteroid impact, no singular catastrophe that can be pointed to as the moment Mars became the cold desert it is today. The transition was driven by several interacting processes playing out over hundreds of millions of years, and understanding those processes requires looking at Mars not as an isolated world but as a planetary body with a specific size, a specific internal heat budget, and a specific position in the solar system. Mars is smaller than Earth. Its diameter is roughly half of Earth's, and its volume is about 15% of Earth's volume. This difference in size has profound consequences for planetary longevity. A smaller planet cools faster. The heat generated by the accretion of the planet and by the radioactive decay of elements in its interior dissipates more quickly into space from a smaller body. Earth's interior is still hot enough to drive active plate tectonics, to keep the outer core liquid and generating the magnetic field, and to fuel volcanic activity that continuously renews the atmosphere and recycles carbon through the rock cycle. Mars, being smaller, ran through its internal heat budget faster. By the time the Noachian ended, the Martian interior was already significantly cooler than Earth's interior at the equivalent stage of Earth's history. The cooling of the Martian interior had 3 cascading consequences that together dismantled the Noachian world. First, volcanic activity declined. The great outgassing that had built the early thick atmosphere slowed and eventually became episodic rather than continuous. The atmosphere lost its principal source of replenishment. Second, the magnetic field weakened and eventually collapsed. Without the liquid outer core convection that generates a magnetic field, the dynamo stopped. The protective magnetic shield that had deflected the solar wind disappeared, and the solar wind began attacking the atmosphere directly. Third, and partly as a consequence of the first two, the atmosphere thinned. Without volcanic replenishment and without magnetic protection, atmospheric gases were lost to space, stripped away by solar wind ions, escaping thermally from the top of the atmosphere, gradually reducing the pressure at the surface below the level required to maintain liquid water. The process was slow. It was not a catastrophe in the geological sense of a sudden transition, but it was, in its ultimate effect, total. The Mars that emerged from the end of the Noachian and the subsequent Hesperian period, settling into what planetary scientists call the Amazonian, the geological era that continues to the present day, is a world where liquid water cannot persist at the surface under normal conditions, where the atmosphere is too thin and too cold to support it, and where surface radiation from cosmic rays and solar particles makes the top meter or so of the Martian soil a hostile environment for the complex organic molecules that life depends on. Underground is a different story, and the script will return to it. But the surface transformation is the dominant fact of Martian planetary history. The Noachian world, with its water and its warmth and its chemical richness, gave way over hundreds of millions of years to the frozen, irradiated, nearly airless desert that the first spacecraft photographs revealed in the 1960s and 1970s. Understanding that transition is essential for understanding what may have happened to any life that existed during the Noachian. On Earth, when environments change, life adapts, migrates, or goes extinct. The same three options would have been available to any Noachian Martian life. Adaptation is possible if the change is slow enough and the genetic variation wide enough. Migration is possible if there are other habitable environments to move to. Extinction is possible if neither adaptation nor migration succeeds. On a planet where the surface was becoming progressively less habitable, while the subsurface retained liquid water and chemical energy for far longer, migration underground, or survival in underground refugia that had existed all along, represents a genuinely viable trajectory. The subsurface of Mars is not empty. It is cold, but cold does not mean sterile. Groundwater may still exist in liquid form deep beneath the Martian surface, kept liquid by residual geothermal heat or by the depression of the freezing point by dissolved salts. The detection of what appears to be a subglacial liquid water layer beneath the South Polar ice cap, reported in analyses of radar data from an orbital mission, represents one of the more provocative recent findings in Mars science. The interpretation is not universally accepted. Alternative explanations involving certain types of clay minerals have been proposed, but the possibility of liquid water existing somewhere beneath the Martian surface today, 4 billion years after the Noachian, is taken seriously by planetary scientists. If liquid water persists underground on Mars today, it persists in conditions that Earth's deep, subsurface biosphere would recognize. The rock is 3 kilometers down, not the surface rock that rovers photograph and drill, not the weathered, radiation-scoured basalt that sits exposed to the Martian sky. This rock is deep, fractured by ancient tectonics and impact stress, saturated in places with water that has not seen the surface in billions of years. The temperature down here is cold by human standards, but not by the standards of the organisms that inhabit equivalent depths on Earth. The pressure is higher. The chemistry of the water in the fractures is concentrated. Salts, dissolved gases, mineral ions leached from the surrounding rock over geological timescales. On Earth, environments like this are inhabited. The deep subsurface biosphere of Earth is one of the most significant scientific discoveries of the late 20th and early 21st centuries. It is not a dramatic discovery in the sense of a single moment of revelation. It accumulated slowly as drilling projects in South African gold mines, Scandinavian granite formations, and deep ocean sediment cores began returning samples that contained living microorganisms far below the surface, far below any zone where sunlight could penetrate, far below where most biologists had assumed life could exist. The organisms found in these environments are not exotic in their basic biochemistry. They use the same genetic code, the same basic molecular machinery, the same fundamental chemistry as surface life. But their metabolisms are calibrated to conditions that would kill most familiar organisms almost instantly. Some of them are extraordinarily slow. Microorganisms in deep continental rock have been found with generation times, the time it takes a cell to divide and produce 2 daughter cells, measured not in hours or days, but in thousands of years. Their energy sources are chemical reactions between water and rock, the reduction of sulfate to sulfide, the oxidation of hydrogen released when water reacts with iron-bearing minerals in a process called serpentinization, the reduction of carbon dioxide to methane. These are ancient metabolic strategies, far older than photosynthesis, older than the oxygen-based respiration that powers most familiar life. They require only rock, water, and a modest chemical gradient to keep running. They do not need the sun. The relevance for Mars is direct and significant. Serpentinization, in particular, has been identified in the Martian geological record. The mineral olivine, which is abundant in Martian basalts, reacts with liquid water to produce serpentine minerals, magnetite, and molecular hydrogen. This process releases energy and produces hydrogen gas, which is a usable energy source for certain types of microorganisms. The detection of serpentinite minerals in ancient Martian terrains confirms that water-rock reactions of exactly this kind occurred on Mars, and if they occurred during the Noachian, when liquid water was widespread, they would have been generating hydrogen across a significant portion of the Martian subsurface, a planetary-scale chemical energy source that required no photosynthesis, no atmospheric oxygen, no surface sunlight. This is the deep habitability argument for Mars, and it is taken seriously in the scientific community for a straightforward reason. It does not require invoking anything that has not already been documented. It requires only that the same processes documented in Earth's deep subsurface — water rock chemistry, serpentinization, radiolysis of water by radioactive minerals — operated on Mars, which the geological record indicates they did. The question is not whether the energy sources existed. They existed. The question is whether any biology arose to exploit them. To approach that question honestly, it helps to spend some time with what we actually know about the origin of life on Earth, because Mars and Earth were, during the Noachian, both young rocky planets of the inner solar system, both receiving the same rain of organic material from space, both working with the same basic planetary chemistry. The differences between them were of degree, not of kind. The origin of life on Earth remains one of the deepest unsolved problems in science. This is not a comfortable admission in a documentary that aims to ground itself in verified fact, but it is the accurate statement of where the science stands. What is known with confidence is that life existed on Earth by at least 3,500,000,000 years ago, and that chemical traces in ancient minerals tentatively suggest biology may have been operating even earlier, possibly by 4 billion years ago or shortly after. The Earth formed approximately 4,540,000,000 years ago. The window between Earth's formation and the appearance of life is, depending on which estimates you accept, somewhere between 500 million and perhaps as little as 100 to 200 million years. That is a geologically short period for chemistry to organise itself into self-replicating, metabolizing cells. Short enough that some scientists have argued it suggests life, once the basic chemical conditions are in place, may arise relatively quickly, within the time frame of the early wet, chemically active period that any young rocky planet in the right orbital zone goes through. If that argument is correct, then early Mars, which had its own wet, chemically active early period overlapping with and preceding Earth's equivalent period, should be considered a genuine candidate for the independent origin of life. The phrase, independent origin, matters here. One of the more unusual aspects of the Mars habitability discussion is that it involves not just the question of whether life could have arisen on Mars, but also the question of whether life could have transferred between Mars and Earth. The mechanism is well established in principle. Large impacts on Mars can eject surface material with enough velocity to escape Martian gravity. Some of that ejected material, in the form of rocks, travels through interplanetary space and eventually reaches Earth, landing as meteorites. This process is documented. Martian meteorites have been found on Earth, recovered primarily from Antarctica, where their dark surfaces stand out against the ice, and their Martian origin confirmed through analysis of trapped gases that match the composition of the Martian atmosphere as measured by landers. More than 300 individual Martian meteorites are known in collections around the world. The transfer of material from Mars to Earth is therefore a confirmed phenomenon. What is not confirmed is whether any living organisms, or any viable biological material, spores, organic molecules associated with biology, genetic material, could survive the journey. The survival problem has several components: the violence of the ejection event itself, the radiation environment of interplanetary space during transit, the heat of atmospheric entry, and the impact with Earth's surface. Laboratory experiments and modelling work suggest that certain types of rock, particularly dense, low-porosity basalt, can shield their interiors from the worst of the radiation during a multi-million-year transit. Certain microorganisms, notably bacterial spores, can survive radiation doses and vacuum conditions far beyond what ordinary living cells could tolerate. The possibility of biological transfer, called lithopanspermia, is not dismissed by mainstream science. It is considered a low probability but non-zero possibility. If life did arise on Mars during the Noachian, and if rocky material from the Martian surface reached Earth during the same broad period, and it would have, because the early solar system was a far more collision-active environment than the current solar system, then the question of whether life on Earth could have Martian ancestors is, strictly speaking, open, not proven, not the leading hypothesis, but not ruled out by the evidence currently in hand. This is not a fringe position. Serious planetary scientists and astrobiologists engage with it as a legitimate if speculative possibility. The reason it deserves more than dismissal is that the timing works. If Mars had life early, and if Mars was launching rocks toward Earth during the same period, and if some fraction of those rocks could have carried viable biology, then the panspermia vector from Mars to early Earth is at least geometrically plausible. Early Earth, during the late heavy bombardment period of approximately 4 billion to 3,800 million years ago, was being struck by impactors from across the inner solar system. Mars would have been contributing to that bombardment in a minor way through ejected surface material. Sitting with that possibility for a moment does not require accepting it as fact. It requires only recognizing that the solar system during the Noachian was a more interconnected place in terms of material transfer than the stable, relatively quiet system of today. Rocks moved between planets. They still do, at a much lower rate. The question of what those rocks may have carried is a question that the science has not yet closed. The Martian meteorites recovered on Earth have been studied intensively for any sign of biological material. The most famous case is ALH SAISP 4001, a meteorite recovered from the Allan Hills region of Antarctica in 1984 and identified as Martian in the early 1990s. In 1996, a team of researchers published a paper in the journal Science, claiming that ALHE 4001 contains several lines of evidence potentially consistent with biological activity. Polycyclic aromatic hydrocarbons, carbonate globules with features resembling those produced by bacteria, and tiny magnetite crystals in a form that on Earth is produced by magnetotactic bacteria. The announcement generated enormous public attention and was addressed directly by the United States President at the time in a public statement about the significance of the finding. The consensus that developed over the following years was skeptical. Each of the features cited as potentially biological was shown to have plausible non-biological explanations. The carbonate globules could have formed through inorganic chemical processes. The magnetite crystals, while similar in some ways to biogenic magnetite, could have been produced abiotically. The polycyclic aromatic hydrocarbons could have been terrestrial contamination introduced after the meteorite arrived on Earth. The scientific community did not converge on a biological interpretation, and the majority position today is that ALH 84001 does not provide confirmed evidence of life. But the majority position is not the unanimous position. A smaller group of scientists has continued to argue, through subsequent publications, that the original findings remain consistent with a biological interpretation, and that the abiotic explanations are not as straightforward as the consensus position implies. The debate over ALH 4001 has never been formally closed, because the kind of evidence that would close it, either a confirmed biological structure or a fully documented abiotic mechanism for producing all the observed features simultaneously, has not been produced by either side. What the ALH 84001 episode illustrates is the difficulty of the detection problem. Biosignatures, the chemical and physical traces that life leaves in rock, overlap in many cases with features that can be produced by inorganic chemistry. The more ancient the rock, the more degraded the potential biosignatures, and the harder the discrimination becomes. This is true on Earth, where the oldest putative biosignatures in the most ancient rocks are also contested. It is true for Martian meteorites analysed on Earth, and it will be true, to a somewhat lesser degree, for the Jezero samples when they eventually reach terrestrial laboratories, because even the most sophisticated instruments will be working with material that is at minimum 3.5 to 4 billion years old, preserved under conditions that were not optimised for biological conservation. The hunt for life in those samples will require ruling out, one by one, every possible abiotic explanation for every observed feature before a biological conclusion can be seriously entertained. That process will take years and will involve laboratories around the world working with the same material and comparing results. It is meticulous, slow, and immune to shortcuts, which is appropriate. The question being asked is one of the most significant in the history of science. The sediment at the bottom of the lake has been accumulating for 11,000 years, not by any human reckoning. There are no humans yet, anywhere, on any world. But the layers are building in a rhythm set by the seasons of this planet. by the annual cycle of freeze and thaw at higher latitudes, by the periodic floods that arrive when the snowpack on the surrounding highlands melts faster than the ground can absorb it. Each layer is thin, perhaps a fraction of a millimetre in a quiet year, perhaps several millimetres in a year of heavy melt. But each layer is distinct, a dark band of fine mineral particles, then a lighter band of coarser sediment, then dark again. The pattern repeats with the regularity of a geological clock. These layers are called varves on Earth. The same word does not exist on this world, but the process that creates them is identical. Seasonal sedimentation in a lake with a clear annual cycle of input. On Earth, varves preserved in ancient lake sediments have been used to count years back into the distant past, because each pair of bands, dark and light, represents 1 year of deposition. The laminated sediments found in ancient Martian crater basins, examined in orbital imagery, and in the data returned by surface missions, show structures consistent with exactly this kind of rhythmic, cyclically deposited layering. What that rhythmic layering implies is duration, not a flash flood, not a single catastrophic event that deposited all the sediment at once and then dried up. A lake that accumulated cyclical laminated sediments was a lake that persisted through many seasons, many years, many cycles of freeze and melt. The thickness of the laminated units found in some ancient Martian crater floors, combined with reasonable estimates of annual deposition rates, suggests that some of these lakes were active for periods on the order of tens of thousands to potentially millions of years. A lake that lasts for 1 million years is not a temporary anomaly in a dry desert world. It is a permanent feature of a landscape, as stable and continuous as a lake sitting in a mountain valley on Earth today. Stability matters for the origin of life, or for the persistence of life once it has arisen, in ways that are not always immediately obvious. Life as we know it is chemically complex. The molecules that carry genetic information, that catalyze reactions, that form the membranes of cells, are not simple. They require specific conditions to assemble and to persist, specific ranges of temperature, specific chemical environments, protection from radiation that would break their molecular bonds, and, critically, time. The origin of life on Earth is estimated to have required somewhere between tens of millions and a few 100 million years of prebiotic chemistry before the first self-replicating systems emerged. A lake that lasts 1 million years provides more time for chemistry to proceed than a lake that lasts a decade. A lake that lasts 10 million years provides more time still. The Noachian crater lakes of Mars were not all equally long-lived. Some may have been relatively brief, filling during wet periods and drying during dry ones, with only thin sediment records to show for their existence. Others, in larger basins with more extensive catchment areas and more reliable water sources, may have been genuinely persistent over geological timescales. Jezero is one of the better documented cases of a long-lived crater lake, but it is not unique. The Eberswald crater in the southern highlands preserves a classic fan-shaped river delta at its inlet, one of the clearest signs in the Martian geological record of sustained, long-duration water flow into a standing lake. The delta at Eberswald was significant enough that it was a finalist landing site for the Curiosity rover mission before Gale Crater was selected. The chemistry arriving at these lake floors from the rivers feeding them was not uniform. Water draining different types of highland terrain would carry different dissolved mineral loads. Volcanic terrain produces water enriched in silica and certain metal ions. Terrain rich in olivine-bearing basalt produces water carrying magnesium and iron. Carbonate-bearing terrain, where it existed, would produce alkaline, carbonate-rich water. The mixing of these different chemical signatures in lake basins would have created chemical gradients, zones where different water types met and reacted, of the kind that are particularly productive for complex chemistry. At the delta front, where river water meets lake water, the sudden change in current velocity causes minerals to precipitate out of solution in characteristic patterns. Iron oxide settling here, silica precipitating there, clays forming in the transition zone between the coarser sediment of the delta and the finer sediment of the deeper lake floor. These precipitation zones are, on Earth, associated with some of the oldest evidence of microbial activity. Banded iron formations, the ancient iron-rich sedimentary rocks that record the early history of Earth's ocean chemistry, are now understood to have formed in part through the activity of iron-oxidizing bacteria that altered the chemistry of shallow marine waters. Siliceous hot spring deposits, like those found in Yellowstone, host thriving microbial communities in their mineral-rich, chemically active waters. the stromatolites of Western Australia, layered structures built by mat-forming cyanobacteria over billions of years, record microbial life organised around shallow, chemically active water bodies. All of these Earth analogues point in the same direction. The type of environment documented in the Noachian crater lakes of Mars is, on Earth, exactly the type of environment associated with early and persistent microbial life. The analogue argument has limits, and those limits should be stated clearly. An analogue shows that the conditions were similar. It does not show that the outcome was the same. Earth produced life in its early lakes and shallow seas. That fact does not logically entail that Mars produced life in its early lakes, even if the conditions were comparable. The conditions were necessary but may not have been sufficient. Some additional factor, a particular concentration of a specific molecule, a particular physical configuration that allowed the first self-replicating system to form, a particular sequence of events, may have been present on Earth and absent on Mars, or may simply have happened on Earth before it happened on Mars, or before Mars lost the conditions that would have allowed it to happen at all. This is the core uncertainty that runs through all serious discussion of early Martian life. It is not uncertainty about the conditions. The conditions are increasingly well documented. It is uncertainty about the process, about whether the origin of life is a near inevitable outcome of the right conditions given enough time, or whether it is a rare event that requires a very specific conjunction of circumstances that may have occurred only once in the history of the solar system, or at most, a handful of times. The answer to that question, which biology and chemistry have not yet produced, determines almost everything else about the probability of life on early Mars. The carbon question is part of this. Carbon is the backbone of all known life. Carbon chemistry, organic chemistry, is the most versatile in the periodic table, capable of forming the complex, stable, information-carrying molecules that life requires. Carbon on early Mars was available in multiple forms: carbon dioxide in the atmosphere, carbonate minerals in the rocks, organic carbon delivered by meteorites and interplanetary dust. The carbon cycle on early Mars, driven by volcanic outgassing and the weathering of surface rocks, was active during the Noachian. Whether that carbon was cycling through any biological systems is the question that the rock record has not yet answered. The detection of methane in the Martian atmosphere has added a layer of complexity and intrigue to the carbon discussion. Several independent detection reports, including data from the Curiosity rover's tunable laser spectrometer, have indicated the presence of methane in the Martian atmosphere at low but detectable concentrations. Methane is significant because on Earth it is produced both by geological processes, serpentinization, and certain types of volcanic activity produce methane, and by biological activity. Methanogenic archaea, a group of microorganisms that produce methane as a metabolic byproduct, are among the most ancient lineages of life on Earth, and are found in environments ranging from deep marine sediments to the guts of cattle. The detection of methane on Mars does not confirm biology. The geological sources, serpentinization, ultraviolet degradation of organic molecules on the surface, reactions between brines and silicate minerals, are sufficient in principle to explain the observed concentrations. But the reports of variability in the methane signal, with apparent seasonal fluctuations and possible localized sources, have kept the discussion open. A purely geological methane source should produce a relatively steady, well-mixed atmospheric signal. Variability and localization are more consistent with, though not proof of, sources that are either heterogeneous in distribution or episodic in output, which is at least compatible with biological activity in specific subsurface environments. The European Space Agency's Trace Gas Orbiter, which began its science operations around Mars in 2018, was specifically designed in part to characterize the Martian methane signal with greater sensitivity and spatial resolution than previous instruments. The results from that mission have been more constraining than expected. In some observation periods, the Trace Gas Orbiter found methane concentrations below its detection limit on days when Curiosity was reporting positive detections from the surface. The discrepancy between orbital and surface measurements has not been fully resolved, and represents one of the more puzzling active problems in Mars atmospheric science. What the methane debate illustrates is the broader challenge of interpreting chemical data from Mars at a distance. The instruments sent to Mars are powerful by the standards of remote sensing, but they are not equivalent to a fully equipped analytical laboratory. They make measurements in specific conditions, at specific times, with specific detection limits, and the data they return require careful interpretation in the context of all the other variables in the Martian environment. The atmosphere of Mars is chemically active in ways that are still being worked out, with ultraviolet radiation driving photochemistry on the surface and in the gas phase, and with the soil chemistry producing oxidants that would rapidly destroy organic molecules exposed to it. That soil chemistry, the presence of perchlorates and other reactive oxidizing compounds in the Martian soil, is one of the more sobering aspects of the modern Martian surface environment. Perchlorates are salts of perchloric acid, and they are distributed across the Martian surface in concentrations significantly higher than in most Earth soils. They were first detected by the Phoenix lander, which touched down in the northern plains of Mars in 2008, and subsequently confirmed at multiple locations. Perchlorates are not fatal to life under all conditions. Some microorganisms on Earth actually use perchlorates as an energy source, but their presence in the surface soil, combined with the intense ultraviolet radiation and the extreme dryness, makes the top layer of the Martian surface an actively hostile environment for the preservation of organic molecules. Beneath the surface, the situation changes. Shielded from ultraviolet radiation by even a meter or two of overlying rock and soil, and in environments where liquid water might persist in brines or hydrothermal systems, the chemical environment becomes substantially less hostile. The subsurface of Mars, from a depth of a few meters down to potentially several kilometers, is the environment most likely to preserve biosignatures from the Noachian, and the environment most likely to harbour any life that may have survived the transition from the wet Noachian world to the cold, dry Amazonian present. The cave systems of Mars represent one specific subsurface environment that has received increasing attention. Volcanic worlds produce lava tubes, tunnels formed when the outer surface of a lava flow cools and solidifies, while molten rock continues flowing beneath, eventually draining out and leaving a hollow tube behind. On Mars, where the lower gravity and the enormous scale of the volcanic provinces suggest that lava tube formation was possible on a grand scale, some of the candidate lava tube structures identified from orbital imagery are potentially much larger than any known on Earth, wide enough, in some estimates, to shelter entire cities from the radiation and temperature extremes of the Martian surface. The interior of a large Martian lava tube would be a substantially more benign environment than the surface, protected from ultraviolet radiation by the rock ceiling, insulated from the extreme temperature swings of the surface, potentially in contact with groundwater or ice in its deeper sections. A large lava tube represents a stable, protected niche. Whether such environments were inhabited during the Noachian, and whether they could still be inhabited today, is a question that future surface missions with drilling or cave entry capability could begin to address. The ice at the South Pole is ancient, not the seasonal frost that forms and retreats with each Martian year, coating the polar cap in a thin white layer of carbon dioxide ice that sublimates back into the atmosphere when the sun returns. Beneath that seasonal layer lies something much older, a stratified deposit of water ice and dust that has been accumulating for hundreds of millions of years, building up in thin annual layers not entirely unlike the sediment varves of the ancient crater lakes, each layer recording something about the climate conditions of the year it was deposited. The south polar layered deposits of Mars extend to a depth of approximately 3.5 kilometers at their thickest point, and they hold a volume of water ice estimated at around 1.5 million cubic kilometers. That is a significant quantity of water. If it were spread evenly across the entire Martian surface, it would form a global layer roughly 11 meters deep. And that is only the water locked in the visible polar ice deposits. Subsurface ice deposits extend across a large fraction of the Martian surface at mid to high latitudes, buried under a thin layer of dust and rock. Radar data from orbital missions have mapped these subsurface ice deposits in considerable detail, revealing sheets of nearly pure water ice extending laterally for thousands of kilometers in some regions. The total water inventory of Mars today, accounting for both polar and subsurface ice, is substantially larger than the surface ice alone suggests. The relevance of this water inventory for the deep history of Mars is that it represents water that never left. Mars did not lose all of its water to space. A significant fraction was locked into the ground as the climate cooled and the surface dried, preserved in a frozen state that has persisted through billions of years of the Amazonian period. Some of that water was originally surface water from the Noachian lakes and rivers, Some was deposited by later events, impacts delivering icy cometary material, volcanic events releasing water vapor that then froze out at the poles and at depth. The ice is a library of Martian water history, and the layered deposits record climate variations across a timescale that dwarfs the entire span of human civilization by a factor of several million. Reading that library requires drilling. The layered polar deposits of Mars have not yet been drilled by any mission. The radar instruments aboard orbiters have revealed the internal structure of the deposits from above, showing the layers as distinct reflective horizons at different depths, but the composition and chemistry of those layers can only be inferred from models rather than measured directly. A future mission capable of drilling into the polar deposits and extracting ice cores, analogous to the ice core drilling programs in Antarctica and Greenland that have revolutionized the understanding of the Earth's past climate, would represent a major advance in Martian climate science. The radar data from the South Polar region produced one finding that has remained among the most discussed results in recent Mars science. A set of observations from an orbital radar instrument reported a bright subsurface radar reflection beneath the South Polar layered deposits at a depth of approximately 1.5 kilometers, extending laterally for roughly 20 kilometers. The brightness and character of the reflection were interpreted by the researchers who published the analysis as consistent with a body of liquid water, a subglacial lake, analogous to the subglacial lakes discovered beneath the Antarctic ice sheet on Earth, the most famous of which, Lake Vostok, has been isolated from the surface for approximately 15 million years and has been found to contain living microorganisms. The interpretation of the Martian radar reflection as a subglacial lake was not universally accepted, and the subsequent years have seen an active scientific debate about what exactly the radar data are showing. The liquid water interpretation requires that the water remain liquid at the base of the polar ice deposits, which, given the current Martian geothermal heat flow, is only possible if the water is heavily loaded with salts that depress its freezing point significantly. Perchlorate salts, for instance, which are already known to be present in the Martian soil and which can depress the freezing point of water by tens of degrees Celsius at high concentrations. An alternative interpretation proposes that certain types of clay minerals or other non-liquid materials could produce radar reflections of similar brightness and character. Additional analyses using extended datasets found multiple bright subsurface reflections in the same region, which complicated the liquid water interpretation somewhat. A single subglacial lake is geologically coherent, but a cluster of separate bright reflections distributed across a wider area is harder to explain by the same mechanism. The debate remains open. What can be said is that the South Polar radar anomaly represents a genuine, unexplained feature of the Martian subsurface, and that the liquid water interpretation, while contested, has not been definitively ruled out. The broader point about Martian subsurface water does not depend on the resolution of the South Polar debate. Even without confirmed present-day liquid water, the geological evidence for deep subsurface liquid water in the geological past is strong. During the Hesperian period, which followed the Noachian and lasted from roughly 3,700,000,000 to approximately 3 billion years ago, enormous catastrophic floods periodically broke out from the Martian subsurface, carving the giant outflow channels that are among the most dramatic geological features on the planet. Channels like Cassi Vallis and Ares Vallis extend for thousands of kilometers across the Martian surface, carved by floods of water, whose estimated peak discharge rates exceed those of any river system on Earth by orders of magnitude. These catastrophic floods were not fed by surface rainfall or snowmelt. They were fed by the release of pressurized groundwater from a deep confined aquifer system, water that had been trapped underground under pressure and that broke through the overlying rock when conditions allowed, perhaps triggered by impacts or by the pressure of overlying ice. The existence of this deep, pressurized groundwater system during the Hesperian is one of the clearest indications that the Martian subsurface held enormous quantities of liquid water long after the surface had dried, and if liquid water persisted in a deep, confined aquifer system through the Hesperian, some fraction of that system may have remained liquid at progressively greater depths, with progressively higher salt concentrations, into the Amazonian period and potentially to the present. The temperature profile of the Martian subsurface is a key variable. The surface of Mars today is bitterly cold. Average surface temperatures are around -60 degrees Celsius. with equatorial daytime highs reaching around 20 degrees Celsius and polar winter lows dropping to minus 140 degrees Celsius or below. But temperature increases with depth, even on a geologically cool body like modern Mars. The rate of increase, the geothermal gradient, is lower on Mars than on Earth because Mars's interior has cooled more. Estimates of the current Martian geothermal gradient suggest that temperatures reach the melting point of pure water ice at depths of somewhere between 6 and 10 kilometers, depending on the local heat flow. With the freezing point depression provided by dissolved salts, liquid water could exist at shallower depths, potentially within the range of a few kilometers from the surface in some locations. A few kilometers is within the range of deep drilling, not the shallow drilling that current Mars rovers perform. Perseverance's rotary percussive drill reaches a depth of a few centimeters to a few tens of centimeters into rock. Not even the MOLE instrument carried by the InSight lander, which was designed to reach 5 meters, but was unable to penetrate the unusual soil properties it encountered and never reached its target depth. Real deep drilling on Mars, the kind that would be needed to sample the potentially habitable subsurface directly, would require a mission of substantially greater mass and complexity than anything yet sent to the planet. It is an engineering challenge of the first order, and it is not part of any currently approved planetary science mission. The InSight lander deserves attention in its own right, because although its primary drilling experiment failed, its seismometer succeeded in recording Martian seismic activity, Marsquakes, providing the first direct measurements of the Martian interior structure. The seismic data revealed a crust thicker than some models had predicted, a mantle with properties that constrain the thermal evolution of the planet, and a core that is liquid, as expected, but larger and less dense than many pre-mission models had estimated. The larger, less dense core implies a core composition richer in lighter elements, sulfur and possibly oxygen and hydrogen mixed into the iron, than Earth's core. A core rich in light elements is consistent with a core that solidified its outer portion earlier in Mars's history, which is consistent with the early collapse of the Martian magnetic dynamo that left the planet without global magnetic field protection. The InSight seismic data also detected what appeared to be 2 meteorite impacts during its operational period, and the seismic waves from those impacts provided additional information about the shallow subsurface structure in the landing region. One of those impacts was later imaged from orbit, revealing a fresh crater with water ice exposed at the surface by the excavation. Ice at relatively low Martian latitudes, closer to the equator than the polar regions, is not expected to be stable on the surface, but it can persist underground even at lower latitudes if buried deeply enough. The exposure of ice by a fresh impact crater at a latitude of roughly 35 degrees north was a direct confirmation that the near subsurface ice inventory of Mars extends significantly beyond the polar regions. What the picture of subsurface Mars adds up to, the radar anomalies, the outflow channel evidence for deep pressurized aquifers, the geothermal gradient estimates, the exposed ice at mid-latitudes, is a planet that is not simply a frozen dead rock, but a planet with a complex internal hydrological legacy, one that has not been fully resolved even after decades of orbital and surface observation. The water that made the Noachian lakes possible did not all disappear to space. Much of it went underground, and some portion of what went underground may still be there in liquid form, in the coldest, saltiest, deepest environments the planet provides. For life, the significance of that picture depends on whether any biology survived the Noachian and found refuge in the subsurface as the surface became hostile. The survivability question is one that extremophile biology on Earth addresses in productive and sometimes surprising ways. Extremophiles, organisms that thrive in conditions that would be lethal to most life, have been found in environments that push nearly every physical and chemical parameter to extremes. In the Atacama Desert of Chile, one of the driest places on Earth, microorganisms survive in the rock itself, sheltered in translucent mineral crusts that let in just enough light for photosynthesis while blocking the desiccating effects of the surface. In the deep Antarctic ice, microorganisms have been found alive in ice that has been frozen for millions of years. In highly acidic drainage water from sulfide mineral deposits, organisms thrive at pH levels close to 0. In the salt crystals of ancient evaporite deposits, claims have been made, contested but not dismissed, of organisms surviving for tens of millions of years in a state of dormancy. The relevance of these Earth extremophiles is not that they prove life exists on Mars. They do not. Their relevance is that they demonstrate the breadth of conditions under which life, once it has originated, can persist. If life arose on Mars during the Noachian, in the warm crater lakes, in the hydrothermal systems, in the chemically active river sediments, then the question of whether it survived the long transition to the cold, dry Amazonian is not automatically answered by the harshness of the surface environment. Life that had access to the subsurface, to the deep brines, to the hydrothermal systems that persisted longer underground than at the surface had options. The biological history of Earth's own extremophile lineages suggests that once life has a foothold, it explores the available chemical and physical space with considerable thoroughness. The deep biosphere of Earth contains, by some estimates, a total biomass comparable to, or exceeding, the biomass of all surface life on the planet. It is invisible to casual observation. It operates on timescales of thousands of years per generation. It makes no noise, produces no signal detectable from space, and would be easily overlooked by any observer who was only looking at the surface. A Martian deep biosphere, if it exists, would be similarly invisible from orbit and similarly undetectable by the instruments currently operating on the surface. Finding it, if it is there, would require going to where it is. The volcanic plain stretches to the horizon in every direction. No wind today, or none strong enough to raise the fine dust that settles here between storms. The light is low and reddish, filtered through a thin haze of airborne particles that never fully settles. The ground underfoot, if there were feet to stand on it, is dark basalt, fractured into angular blocks by the thermal cycling of 4 billion years of warming and cooling. In the distance, barely visible through the haze, the western flank of a shield volcano rises so gradually that it looks less like a mountain than like the horizon itself tilting upward. The volcano is Olympus Mons, the largest volcanic structure in the solar system, and it is not yet finished. During the Noachian and Hesperian periods, it was actively erupting, adding layer after layer of basalt to its enormous flanks in eruptions that released not just lava, but vast quantities of volcanic gas, sulfur dioxide, water vapour, carbon dioxide, hydrogen sulfide, directly into the atmosphere. The volcanic history of Mars is inseparable from the history of its atmosphere and its water, and therefore inseparable from the history of its potential habitability. Understanding what Mars's volcanoes did, over what timescale and what they left behind, is essential for understanding why the early Mars was the world it was, and why the transition away from that world was so total. Olympus Mons today stands approximately 22 kilometers above the mean surface elevation of Mars, making it roughly 2.5 times the height of Mount Everest above sea level. Its base diameter is approximately 600 kilometers, wide enough that if you stood at its center, the edges would lie beyond the horizon due to the curvature of the planet. It is a shield volcano, built from low viscosity basaltic lava that flowed great distances before solidifying, building up the broad, gently sloping structure rather than the steep-sided cone of a more explosive volcanic type. The youngest lava flows on its surface are geologically recent, within the last few tens of millions of years, suggesting that Olympus Mons may not be entirely extinct even today. But the volcanic activity of Mars during the Noachian was not limited to Olympus Mons. The entire Tharsis volcanic province, a region of elevated terrain roughly the size of North America, was building during this period, and the scale of the volcanic outgassing associated with the construction of Tharsis has been estimated as extraordinary. Models of Tharsis formation suggest that the total volume of volcanic gas released during the construction of this province was sufficient to have produced an atmosphere several times thicker than Earth's current atmosphere, had all of it been retained. In practice, much of it was lost over geological time to space and to reaction with surface minerals, but during the active construction phase, the volcanic contribution to atmospheric thickness was dominant. The sulfur dioxide released by Martian volcanism deserves particular attention because of its dual role in the early Martian climate and chemistry. On one hand, sulfur dioxide is a greenhouse gas that would have contributed to warming the surface and keeping it above the freezing point of water. On the other hand, sulfur dioxide reacts with water in the atmosphere to produce sulfuric acid aerosols, which are highly reflective and would have cooled the surface by reflecting incoming sunlight back to space. The balance between these warming and cooling effects of volcanic sulfur dioxide is a significant area of active modelling in Martian climate science, and the outcome of the balance, whether volcanic eruptions net warmed or net cooled the early Martian surface, depends on eruption rates, atmospheric composition, and other variables that are difficult to reconstruct with precision. What the geological record preserves from this volcanic activity is sulfate minerals. Sulfur-bearing minerals formed when sulfur dioxide reacted with water and rock at the surface. The Hesperian period in particular is characterized by the widespread deposition of sulfate minerals across the Martian surface, and these sulfate-bearing layers are directly visible in the stratigraphy of locations like Meridiani Planum, where the Opportunity rover spent nearly 15 years examining the exposed rock record, and Gale Crater, where Curiosity has read through a sequence of sedimentary layers representing the environmental transition from the wetter Noachian into the more acidic, sulfate-dominated Hesperian. The transition captured in those sedimentary layers is one of the most clearly documented environmental shifts in Martian geological history. At the base of the sequence, the oldest layers, the minerals are the phyllosilicates, the clays, that formed in the neutral to slightly alkaline liquid water of the Noachian. Moving upward through the sequence, toward younger and younger rock, the clay minerals give way to sulfate minerals, reflecting the acidification of the water environment as volcanic sulfur dioxide became a more dominant influence on surface chemistry. The transition from clay-dominated to sulfate-dominated chemistry marks the shift from a Mars where water was relatively benign for organic chemistry to a Mars where the water, where it existed, was substantially more acidic and chemically aggressive. This acidification of the late Noachian and early Hesperian water environment is relevant to the life question in an important way. Acidic environments are not necessarily sterile. There are acid-tolerant and acid-loving organisms on Earth, and some of the most productive microbial ecosystems in volcanic regions operate in highly acidic conditions. But the specific shift documented in the Martian record, from near-neutral clay-forming water to acidic sulfate-forming water, represents a change in the chemical landscape that would have placed selective pressure on any biology present. Life that had adapted to the neutral water chemistry of the Noachian crater lakes would have had to adapt to the new, more acidic chemistry of the Hesperian, or retreat to environments where neutral or alkaline water still persisted, deep groundwater systems, for instance, which would have been buffered from the surface acidification. The deep groundwater of Mars during the Hesperian would have been substantially more insulated from the changing surface chemistry than the lakes and rivers. Water that had infiltrated deep into the rock during the Noachian and that circulated slowly through fractured basalt at depth would have equilibrated with the surrounding rock chemistry rather than with the surface atmosphere. Basalt is a buffering material. It reacts with acidic water to neutralize it, producing the clay minerals and carbonate minerals that record this neutralization in the rock. Deep groundwater circulating through basalt would therefore have maintained a more neutral chemistry, even as the surface environment acidified, providing a potential refuge for any life that had colonized the subsurface during the more hospitable Noachian. The carbonate mineral record of Mars is worth examining here, because it relates directly to the question of what the deep water chemistry was like, and because it has produced some surprising findings. Carbonates, minerals like calcite and magnesite, form when carbon dioxide reacts with calcium or magnesium in the presence of water, and they are a major component of the geological record of water chemistry on Earth. On early Mars, given the carbon dioxide-rich atmosphere and the abundant liquid water of the Noachian, one might expect carbonates to be a prominent component of the sedimentary record. The relative scarcity of carbonates in the Martian surface record compared to what might be expected has been one of the more puzzling features of Martian geochemistry. The explanation most consistent with the available data is that the Noachian surface water was acidic enough, from dissolved carbon dioxide, from volcanic sulfur dioxide, or from both, to prevent the stable precipitation of carbonate minerals in most surface environments. Carbonate precipitation requires water with a pH above a certain threshold. Below that threshold, the carbonate dissolves rather than precipitating. If the surface water of the Noachian was consistently on the acidic side of neutral, carbonates would have been absent from most surface sediments, even while forming in more sheltered alkaline environments. Carbonate minerals have, however, been detected on Mars in specific contexts. The Mars Global Surveyor mission detected carbonate-bearing rocks in the ancient terrains of the Nili Fossae region, a geologically complex area northeast of the Isidis Impact Basin. The Nili Fossae region is one of the most mineralogically diverse areas on Mars, hosting a range of clay minerals, carbonates, and olivine-bearing rocks that together suggest a complex history of water-rock interaction spanning multiple geological periods. The carbonates here likely formed in an environment where the water was more alkaline than the average surface condition, perhaps in a hydrothermal system or in a subsurface setting where the buffering capacity of the surrounding rock kept the pH in the range where carbonates could precipitate. The Phoenix lander, operating in the northern plains in 2008, also detected carbonate minerals in the surface soil at concentrations of a few percent by weight. This was a significant finding because it suggested that carbonate formation had occurred at some point at high latitudes, perhaps during periods of higher atmospheric humidity when thin films of liquid water formed on the soil surface, reacting with atmospheric carbon dioxide. The amounts detected were small, but the presence of carbonates in the soil, a surface environment where acidic conditions should have prevented their formation, points to a more chemically complex history than a simple acid-dominated model would predict. The olivine carbonate association in the Nili Fossae is particularly interesting from an astrobiological standpoint. Olivine reacting with water produces serpentine minerals and releases molecular hydrogen through serpentinization. In environments where serpentinization is active, the local water chemistry becomes strongly alkaline as the reaction proceeds, and this alkaline water is favourable for carbonate precipitation. The same environments where serpentinization was generating hydrogen as a chemical energy source for potential life would also have been generating the alkaline carbonate precipitating water chemistry recorded in the Nili Fossae rocks. The co-occurrence of these features, energy source, alkaline water, carbonate precipitation, in a single geological setting is the kind of convergence that makes astrobiologists pay attention. Nili Fossae was, like Eberswalder, a finalist landing site for the Curiosity mission. It was ultimately not selected in part because of concerns about the engineering challenges of landing in a geologically diverse, topographically complex region. It remains one of the highest priority sites for future Mars surface investigation, precisely because its mineral diversity encodes such a rich record of past water chemistry and potential habitability. The broader Isidis Basin region, within which Nili Fossae sits at the northwestern rim, is itself an ancient impact structure that has been deeply modified by subsequent geological processes, including volcanism, water activity, and tectonic deformation. The Isidis Basin formed during the period of heavy bombardment, making it one of the oldest large impact features on Mars. Its floor has been partly resurfaced by younger volcanic material, but its margins preserve some of the most ancient and mineralogically intact terrain on the planet. Studying the margins of Isidis is, in a sense, reading the oldest surviving chapters of the Martian geological record. Impact craters are not merely holes in the ground, they are chemical factories. When a large impactor strikes a rocky planet, the energy released vaporizes and melts enormous volumes of rock, creating a temporary magma pool at the impact site. This impact melt cools over thousands to tens of thousands of years, and during that cooling period it interacts with any water in the target rocks, creating a hydrothermal system that can persist for geologically significant periods. The largest impact craters on Mars, Hellas Arga Isidis, would have generated hydrothermal systems of enormous scale following their formation, systems that could have operated for millions of years as the impact melt cooled. These impact-generated hydrothermal systems are increasingly recognized as potentially important environments for prebiotic chemistry and early life, both on Earth and on Mars. The connection between large impacts and hydrothermal habitability represents one of the more counterintuitive aspects of the early Mars habitability picture. Impacts are destructive. The energy released by a large impact is sufficient to sterilize the surface of a planet over a wide area, and the period of heavy bombardment that affected all the inner planets between roughly 4,100 million and 3,800 million years ago was, in one sense, a hostile environment for any life attempting to establish itself. But in another sense, each large impact created a new hydrothermal environment, a warm, chemically active, water-rich system that could have served as a fresh start for biology or as a new ecological niche for life that had survived the impact event in the surrounding terrain. On Earth, the deep subsurface biosphere would have survived even the most severe impact events of the heavy bombardment period, sheltered by kilometers of overlying rock from the worst of the surface devastation. The same logic applies to Mars. The dust storm has been building for 3 days. It started, as most global Martian dust storms do, as a regional disturbance in the southern hemisphere during the southern summer. When Mars is near perihelion, its closest approach to the Sun, and the increased solar heating drives stronger convective activity in the lower atmosphere. Dust lifted from the surface absorbs sunlight and warms the surrounding air, which rises and draws in more air from the sides, lifting more dust, warming more air. The feedback loop, once established, can escalate a regional storm into a planet-encircling event within a matter of weeks. When a global dust storm reaches full development, it can reduce surface solar irradiance to a small fraction of its clear sky value, dropping temperatures at the surface while paradoxically warming the middle atmosphere where the dust is absorbing the most sunlight. The dust storms of modern Mars are among the most dramatic meteorological events in the solar system. They have ended missions. The Opportunity rover, which had operated for nearly 15 years on the Martian surface, went silent in June of 2018 when a global dust storm reduced sunlight below the level needed to keep its solar panels charged, and it never woke up again. They have constrained mission planning for every solar-powered spacecraft sent to Mars, and they have revealed something important about the Martian atmosphere. It is dynamic, responsive, and capable of behaviour that simple models do not fully capture. The dust that drives these storms is the surface layer of Mars, the fine iron oxide-rich particles that give the planet its characteristic colour. This dust is not uniformly distributed. It has been moved, sorted, deposited, and reworked by wind and by the seasonal carbon dioxide frost cycle over billions of years. In some regions, it lies in thick blankets dozens of meters deep. In others, it has been stripped away by wind to expose the underlying bedrock. The dust carries a chemical record of Mars's surface history: oxidized iron minerals, perchlorate salts, fine silicate particles, and it coats every surface it encounters, including the solar panels of spacecraft and the optical systems of cameras. The story of how Mars came to have its current dust-covered red surface is itself a piece of planetary history that connects back to the wet Noachian world. The iron oxides that colour the dust formed primarily through the oxidation of iron-bearing minerals, olivine, pyroxene, magnetite, during the Noachian and Hesperian periods when liquid water was available to drive the weathering reactions. The red of Mars is, in this sense, a chemical memory of the ancient water. Every dust particle carrying that reddish iron oxide colour was once part of a rock that was weathered in the presence of liquid water, billions of years ago. The colour of the Martian sky, the butterscotch haze that Martian landers photograph, is sunlight scattered and absorbed by these iron oxide dust particles suspended in the thin atmosphere. Understanding the current Mars environment matters for the question of habitability, not because the current surface is habitable, it clearly is not for most forms of life, but because the processes operating today provide constraints on what has happened in the geological past and on what the subsurface environment may be like. The dust storm cycle, for instance, drives a seasonal redistribution of water vapour in the Martian atmosphere, with implications for where subsurface ice is stable and where it is not. The carbon dioxide frost cycle, which deposits a seasonal layer of dry ice at the poles each winter and releases it each spring, drives a global pressure cycle. The atmospheric pressure at any given point on Mars fluctuates by roughly 25% over a Martian year as carbon dioxide moves in and out of the polar ice caps. This pressure cycle would have been different on early Mars, when the atmosphere was thicker and carbon dioxide ice at the poles would have played a different role in the overall climate system. The early Martian climate is in many ways a more complex system to model than the current one, because it involves more variables in a more interconnected way. The greenhouse warming from the thicker atmosphere, the cooling from volcanic aerosols, the hydrological cycle driven by precipitation and evaporation, the albedo effects of surface ice and dust, all of these interacted in ways that climate models are still working to capture accurately. One of the persistent puzzles of early Martian climate modelling is what has been called the faint young sun problem as applied to Mars. The sun was significantly less luminous in the early solar system than it is today, roughly 70 to 75% of its current luminosity during the Noachian. At that reduced solar output, even with a thicker carbon dioxide atmosphere, climate models struggle to keep the surface of Mars above freezing on a global annual average basis. The greenhouse effect of carbon dioxide alone, even at pressures much higher than current estimates suggest were achievable, is insufficient to raise global average temperatures above the freezing point of water under the faint young sun. Several solutions to this problem have been proposed. Additional greenhouse gases, methane, hydrogen, sulfur dioxide, nitrous oxide, could have supplemented the carbon dioxide greenhouse effect. The problem with each of these gases is that they have limited lifetimes in the Martian atmosphere under the ultraviolet radiation environment of the early sun, and replenishment from volcanic sources would need to have been rapid and continuous to maintain significant concentrations. Hydrogen gas in particular has attracted attention as a possible supplementary greenhouse gas because molecular hydrogen has a collision-induced absorption effect in carbon dioxide-rich atmospheres that can provide warming beyond what each gas provides independently. If volcanic outgassing maintained significant hydrogen concentrations in the early Martian atmosphere, the combined greenhouse effect of carbon dioxide and hydrogen could potentially have kept surface temperatures above freezing more consistently than carbon dioxide alone. Another possibility, increasingly favoured by some climate modellers, is that the Noachian warm periods were episodic rather than continuous, that the baseline climate of early Mars was actually cold and icy most of the time, with periodic warmer episodes triggered by large volcanic eruptions or large impact events that temporarily thickened the atmosphere and raised surface temperatures enough to melt ice and generate the liquid water recorded in the geological features. This episodic warm period model does not require the faint young sun problem to be solved globally. It only requires that warm periods were frequent enough and long enough to carve the valley networks, fill the crater lakes, and deposit the clay minerals that the geological record documents. If the episodic model is correct, then the early Mars was not a consistently warm, wet world, but rather a predominantly cold, icy world punctuated by relatively brief warm episodes lasting thousands to tens of thousands of years each. The valley networks and crater lakes would have formed during these episodes. Between episodes, the surface would have been frozen, with most water locked in ice and any liquid water confined to subsurface environments where geothermal heat kept it from freezing. This model has significant implications for the life question. A world that is habitable only episodically at the surface but continuously habitable in the subsurface is a world where any life that established itself in the subsurface would have had a strong selective advantage over life that depended on the surface. The episodic warm period model also helps explain one of the other puzzling features of the Noachian geological record: the apparent coexistence of indicators of liquid water with indicators of cold, icy conditions. Glacial features, landforms consistent with ice sheet flow, with freeze-thaw cycles with periglacial processes, are found in the ancient Martian highlands alongside the valley networks and crater lake deposits. Some researchers have interpreted this as evidence that parts of Mars were glaciated even during the wettest periods of the Noachian, with liquid water and ice coexisting in different regions or at different elevations, much as they do today in high altitude or high latitude regions of Earth. The elevation gradient on Mars is relevant here. The Martian topography has an enormous range. From the bottom of the Hellas Basin, the deepest point on the planet, to the summit of Olympus Mons, the difference in elevation is approximately 30 kilometers. This topographic range creates significant differences in atmospheric pressure and temperature between different regions. During the Noachian, the lower-lying regions, the northern plains, the floors of large impact basins, would have had thicker atmospheric columns and higher atmospheric pressures than the highland terrain. Liquid water would have been more easily sustained at lower elevations, while the highlands may have been predominantly glaciated. The drainage of meltwater from highland glaciers and snowpacks into lowland lakes may have been the primary mechanism feeding many of the valley networks and crater lake systems, rather than rainfall directly onto the lake catchment areas. This glacial meltwater model for the Noachian hydrological cycle is consistent with the branching valley network morphology in some regions, while also explaining the glacial features found in the highlands. It does not require the entire Martian surface to have been warm enough for open precipitation and evaporation cycles, which helps with the faint young sun problem. Instead, it requires only the ice accumulated in the highlands, melted sufficiently at the margins to generate runoff, and fed the lowland lake systems through river systems, cutting down from the glacial margins. The habitability implications of the glacial meltwater model are not dramatically different from those of the warmer, wetter model. The crater lakes and river sediments that are the primary targets for biosignature investigation exist in both scenarios. The hydrothermal systems in volcanic regions were active regardless of the surface climate model chosen. The deep subsurface remained a candidate for continuous habitability across all climate scenarios. What the glacial meltwater model changes is the picture of the surface habitability, making it patchier, more seasonal, more dependent on proximity to glacial margins, rather than the subsurface habitability picture, which depends primarily on geothermal heat and the depth of the permafrost layer. The permafrost of Mars, the layer of permanently frozen ground that underlies most of the Martian surface today, and that has underlain it for most of the Amazonian, represents one of the most significant boundaries in the Martian habitability discussion. Above the permafrost, temperatures cycle dramatically between day and night and between seasons, and any liquid water that forms is quickly frozen or evaporated. Below the permafrost, temperatures are more stable, pressure is higher, and any liquid water present is protected from the surface environment. The permafrost layer acts as both a barrier and a seal, a barrier preventing surface water from reaching the deep subsurface, and a seal preventing deep subsurface water from reaching the surface. During the Noachian, the permafrost layer would have been thinner or absent in the warmer periods, allowing direct communication between the surface water and the subsurface. As the climate cooled through the Hesperian and into the Amazonian, the permafrost thickened progressively, first insulating the deep groundwater from the surface, and then building up the pressure in the deep aquifer system that eventually released catastrophically as the outflow channel floods. The thickening permafrost effectively sealed the subsurface off from the surface, creating an increasingly isolated underground world that has been developing on its own, geochemically and possibly biologically, for billions of years. That sealed underground world is the final frontier of Mars exploration, and it remains, at this point in the history of planetary science, almost entirely unexplored. The sample tube is sealed. It is a small cylinder of titanium, roughly the size and shape of a thick marker pen, and it contains a core of rock drilled from the delta sediments of Jezero crater. The rock inside it is approximately 3.5 to 4 billion years old. It was deposited at the edge of a lake that no longer exists, in a crater that has been dry for longer than multicellular life has existed on Earth. The tube sits on the surface of Mars, cached in a carefully surveyed location, waiting for a retrieval mission that has not yet launched. Around it, the Martian wind moves fine dust across the plain in slow, thin sheets. The sky above is the colour it has been for billions of years. Nothing moves except the dust. Perseverance has cached dozens of these tubes across the Jezero landing ellipse, each one containing a different sample. Delta sediment, igneous rock from the crater floor, atmospheric gas, regolith. Together they represent the most carefully selected collection of extraterrestrial geological material ever assembled, chosen specifically for the locations and rock types most likely to preserve evidence of ancient habitability and, if it ever existed, ancient life. The Mars Sample Return Mission, a joint effort between NASA and the European Space Agency, is designed to retrieve these cached samples and deliver them to Earth for analysis in terrestrial laboratories. The mission architecture has gone through several redesigns as costs and timelines have been reassessed, and as of the current state of planetary science planning, the timeline for sample return has been pushed further into the future than originally anticipated. The delay is frustrating to the scientific community that has been building toward this moment for decades. The logic of sample return is straightforward. The instruments that can be sent to Mars on a spacecraft, however sophisticated, are constrained by mass, power, and volume in ways that ground-based laboratory instruments are not. A gram of Martian sediment analysed in a terrestrial laboratory with a full suite of modern analytical chemistry, mass spectrometry, isotopic analysis, nanoscale imaging, organic chemistry profiling, yields orders of magnitude more information than the same gram analysed by a rover instrument. The difference is not incremental. It is the difference between reading a page through frosted glass and reading it under a magnifying glass in good light. The specific analyses that matter most for the life question are the ones that require the most sensitivity and the most sophisticated instrumentation. Searching for biosignatures, chemical or structural signs of past biological activity, in ancient sedimentary rock requires distinguishing between organic molecules produced by life and those produced by inorganic chemistry, between mineral structures formed by biological processes and those formed by abiotic ones. These distinctions are often subtle, and they require multiple independent lines of evidence pointing in the same direction, before a biological interpretation can be seriously entertained. The history of biosignature research on Earth, where researchers have access to ancient rocks and the full suite of laboratory tools, shows how difficult this discrimination can be even under optimal conditions. The stromatolites of the Pilbara region in Western Australia are a case in point. These structures, preserved in rocks approximately 3,500,000,000 years old, are among the oldest claimed evidence of life on Earth. For decades they were accepted as genuine microbial structures built by mat-forming microorganisms in shallow coastal water. Then, a series of detailed studies showed that some of the structures previously interpreted as biogenic could have formed through purely inorganic processes. Hydrothermal silica precipitation, for instance, can produce layered, dome-shaped structures that superficially resemble stromatolites. The debate about which of the ancient Pilbara structures are genuinely biogenic and which are abiotic has continued for years and has not been fully resolved. If that level of ambiguity exists for ancient Earth biosignatures, studied in terrestrial laboratories with every available tool, the challenge for ancient Martian biosignatures, more degraded, more extensively altered by billions of years of radiation and chemical weathering, studied first by rover instruments and only later by laboratory instruments on a different planet, is formidable. The science community's approach to this challenge is methodical. Collect the most promising samples, preserve them carefully, return them to Earth, and then apply the most rigorous analytical protocols available to the question of whether any feature in any sample requires a biological explanation. What would a confirmed Martian biosignature actually look like? The answer depends on the type of life and the type of preservation, but several categories of evidence are considered most diagnostic. Morphological biosignatures, preserved physical structures of cells or cell colonies, are the most visually compelling, but also the most easily mimicked by inorganic chemistry. Chemical biosignatures, organic molecules in patterns that are specifically associated with biological activity such as the preferential use of certain carbon isotope ratios or the production of specific lipid molecules, are more chemically specific but require extremely sensitive detection. Isotopic biosignatures, patterns in the ratios of stable isotopes of carbon, sulfur or nitrogen that reflect the selective chemistry of living systems, are among the most robust indicators of past biological activity on Earth, and are a primary target for laboratory analysis of return samples. The carbon isotope ratio is particularly important. Living systems preferentially use the lighter isotope of carbon, carbon-12, over the heavier carbon-13, because the lighter isotope reacts slightly faster in enzymatic reactions. This preference leaves a chemical signature in organic carbon associated with life. It is isotopically lighter, depleted in carbon-13 relative to the abiotic baseline. When organic carbon preserved in ancient rocks on Earth shows this depletion, it is one of the strongest chemical indicators of biological origin available to geochemists. The same analysis applied to organic carbon found in Martian sediments. If organic carbon is present in sufficient quantities and sufficiently well preserved in the returned samples, would provide a direct test of biological origin that is difficult to explain by purely inorganic chemistry. The sulfur isotope system provides a complementary line of evidence. Certain types of bacteria that use sulfate as an electron acceptor in their metabolism, the sulfate-reducing bacteria, produce characteristic patterns in the 4 stable isotopes of sulfur that are not reproduced by any known inorganic process. If Martian sediments show sulfur isotope patterns of this kind, it would constitute strong evidence for biological sulfur cycling at some point in the sample's history. The sulfate-rich environments of the Hesperian, documented in the sedimentary record at multiple locations, would have been particularly favourable environments for sulfate-reducing organisms if any were present. The nitrogen isotope system is less straightforward to interpret in the Martian context, partly because the nitrogen inventory of Mars and its history of atmospheric escape complicate the baseline against which any biological signal would need to be measured. But nitrogen-bearing organic molecules, amino acids, nucleobases, porphyrins, if detected in preserved form in the returned samples, would be among the most compelling indicators of past biological chemistry, regardless of the isotopic analysis, because these molecules are the specific building blocks of the informational and catalytic systems that life uses. The organic chemistry of the Jezero Delta sediments, when analysed in terrestrial laboratories, will tell a story about what chemistry was happening in that lake 4 billion years ago. Whether that story includes life is not yet known, but the chemical vocabulary available for reading it is sophisticated, and the samples being collected are from the environments considered most likely to have preserved any biological signal that was present. While the sample return mission remains the most scientifically powerful tool available for the life detection question, it is not the only path being pursued. Several Mars mission concepts under study or development target subsurface access more directly than current rovers. A drilling mission capable of reaching several meters below the surface, deep enough to pass through the radiation damage zone where organic molecules are destroyed by cosmic rays, would access material that has been shielded from the surface environment for potentially very long periods. At a depth of just 2 meters, the radiation dose rate drops to a level where certain types of organic molecules could survive for hundreds of millions of years. At 5 meters, survival over billions of years becomes feasible for the most radiation-resistant compounds. The radiation environment of the Martian surface is one of the most significant challenges for the preservation of biosignatures in near-surface rock. Without a global magnetic field, and with only a thin atmospheric column to absorb incoming radiation, the Martian surface receives a flux of cosmic rays and energetic solar particles that is far higher than Earth's surface receives. The Curiosity rover's radiation assessment detector measured the radiation environment during the cruise to Mars and on the surface, providing the first direct measurements of the radiation dose rate at the Martian surface. The results confirmed that the top meter or so of the Martian surface is a hostile environment for organic molecule preservation on geological timescales. This does not mean that no organic material survives near the surface. The detection of organic molecules by Curiosity in the ancient mudstones of Gale Crater, at a depth of only a few centimeters of drilling, demonstrates that some organics do survive. But the suite of molecules detected is limited, and the question of what may have been lost to radiation over billions of years cannot be answered from surface measurements alone. Drilling deeper is the straightforward response to this problem, and it is one of the driving scientific motivations behind concepts for future subsurface access missions. The planet that those future missions will arrive at is, in important ways, better understood than the planet that the first orbiters photographed in the 1960s. The orbital coverage of Mars is now nearly complete at useful resolutions. The major geological units have been mapped and characterized. The mineral inventory of the surface has been assessed from orbit using infrared spectroscopy. The internal structure has been constrained by seismometry. The radiation environment has been measured directly. The atmospheric chemistry has been sampled by multiple landers and rovers. The water inventory in polar ice and subsurface deposits has been mapped by radar. What has not been done is reach below the surface in any meaningful way, and what has not been answered is the life question. The ancient delta at Jezero still holds its sediment in the flat afternoon light of a Martian day that is 24 hours and 37 minutes long, slightly longer than an Earth day, close enough that early mission planners found the similarity convenient. The wind picks up briefly across the delta plain and then settles. The cached sample tubes sit in their known locations. In the ancient rock of the delta face, the laminated layers that record thousands of years of lake sedimentation are exposed in cross-section where erosion has cut through them, reading left to right like lines of text in a language that no one has yet fully learned to decode. What those layers contain, whether purely the chemistry of an ancient sterile lake or something more, is the question that has driven planetary science for the better part of a century and that will drive it for decades more. The honest answer, at this moment, is that we do not know. The geological evidence for an early Mars that was wet, warm and chemically active during the period when life was either just beginning on Earth or had not yet begun is solid. The case for the early Martian environment being capable, in principle, of hosting life is well supported by multiple independent lines of geological and chemical evidence. The case for life having actually existed there is not yet made. It may be made by the returned samples. It may require a deeper mission. It may remain unmade for a very long time. The permafrost seals the deep subsurface. The dust covers the ancient lake beds. The titanium tubes wait in the thin Martian air. Somewhere below the surface of this planet, at a depth that no instrument has yet reached, chemistry has been running for 4 billion years in liquid water that has not seen daylight since the Noachian ended. Whether anything is alive in that water, using the hydrogen produced by serpentinization as an energy source, cycling sulfur through ancient metabolic pathways, dividing once every 10,000 years in the cold and the dark, that question is genuinely open. Not open in the way that fringe claims are open, where the evidence is absent and the idea is kept alive by wishful thinking. Open in the way that careful, well-supported scientific inquiry is open, when the evidence available is real and compelling, but not yet sufficient for a conclusion. The story of what existed on Mars before anything lived on Earth is still being read. The pages are made of rock, and the reading is slow, and what comes next depends entirely on our willingness to go back and look deeper. If you have stayed with this documentary to its end, you have spent time with one of the most significant open questions in science. Not a mystery invented for dramatic effect, but a genuine, evidence-grounded uncertainty that working planetary scientists engage with every day. Subscribe if you want more documentaries like this one, and rest well.